Welcome back. Today we're going to talk about my favorite topic, and that is interrupts. And we're going to introduce a complication that we sort of glossed over in 319K. It was a problem, but we sort of led you around it so it didn't show up, and that is a critical section. All right, so Lab 2 has got a bunch of stuff in it, one of which is interrupts. Okay? And so what I'd like to do is just generalize the definition of what the world calls as threads. Okay? And so a thread is the execution of software. So if we think about software, okay, and this is a typical main program, the thread is either the sequence of instructions or the action caused by software. Okay? And so if we were to look at what this does, we could sort of, the reason why it's called a thread, and that is if I take my pen and I start at the reset vector and I start executing, right? I go around and around in the loop, and I don't ever pick up my pencil. See that? I don't ever pick it up unless it crashes. No. What else? Unless what? I'm branched. Okay, fine. He wants to put in a. Okay, fine. Let's do it again.
If it gets interrupted.
Yeah, that's the word I was looking for. Interrupts. All right. So if I have a subroutine call, okay. Okay, so this is again a single threaded environment where I'm going to come down here, go there, right? You see that? I can still draw the execution of this thread by not lifting up my pencil. Okay? And in a thread, we can think of there being registers, right? Associated with that thread, we can think of there being a stack. So each thread has its own ownership. Unless someone pointed out what happens on an interrupt. If we have an interrupt, we have a two-threaded system. Okay? The question, the essence of a thread is every time I have to pick up my pen, a new thread is created. Okay? And so if I'm in this loop and an interrupt happens, I have to break that thread, execute this thread, break it again, and continue. You see? You see that? So I'm going to continue this thread. But when a second interrupt happens, okay, I got to break it again. That's thread 1, and I'm going to now have a new thread. Okay? And execute this until I go back there. And so every time an interrupt happens, I legally have another thread because the registers in the stack associated with instantiation 2 and 3 are different, right? Register R1 when I execute the interrupt the first time is different than R1 the second time. So legally, I have multiple threads. Here's a fun one. All right, think about what I just drew. Okay? What do they look like? These flowcharts look like what? In the context of 445L, the flowchart that looks like this is what kind of program? Does it ever return? No. So what kind of program have we written in 319K and 445L that never returns? A main. Yeah, it's a while loop. Right? These are main programs. And you go, hey, John, how can I have more than one main program? How can I have more than one main? I can have more than one main if I have an operating system. Okay? And this is the essence of 445M, the real-time operating system course taught in the spring. And that allows you to have multiple names. And so we are going to have we are going to have, in this case, 3 threads. One executing this one executing this one, and one executing this one, and we're going to run them all concurrently. And we're going to have 3 stacks and 3 registers, and we're going to have 3 of everything. And we're going to need a way to switch from one to the other. And that'll be the essence of the thread switcher. So in this case, here's an interesting sidebar. What can you tell me is a thread equal to a program? No, a thread is not a program. These 3 programs here may be exactly the same one. These 3, the machine code for this, and that may be the exact same machine code, but I'm executing it 3 times. Right? I want to, think of you're going to dig a hole, right? And so embedded in your mind is how to use a shovel, right? So you have a shovel routine that knows how to dig a hole. And if I want to dig 3 times faster, I get 3 people and I make them all run together. And I'm digging the hole 3 times faster. Here's another example. If you think of a window on your computer, a window accepts mouse input, commands, graphics. That same program that controls a window will control all the windows. And you might have multiple windows open, right? Your program might be running multiple times. And so that's the essence of a thread. And so in this class, we're going to call the background thread the interrupt service routine, and we're going to call the foreground thread the main program. And we'll have 1 foreground and multiple background threads. All right, interrupts on this machine are controlled by the nested vectored interrupt controller. It's got some weirdness. How we enable and disable this is a little bit weird, so watch it. We don't use the same register to enable an interrupt as we use to disable it. How we acknowledge is a little weird. How can we create it and clear it? There's a bunch of weirdness, so data sheet makes sense. Again, this is all described here in Chapter 4. Okay. Priority is going to be a big deal. And there's a register, we saw it last time, that has your base priority. So if you're running at priority 3, that means you're running an interrupt service routine out of priority 3. A 0, a 1, or 2 can interrupt you, but a 3, 4, 5, 6, or 7 cannot interrupt you. It's not disbanded, it's not discarded, it's just postponed. So a priority 4 interrupt just will not interrupt a priority 3 interrupt. It just has to wait. Okay? So it's postponed and not dismissed. Yeah, question.
Is it true even if the lower priority interrupt is listed with the start critical and end critical? Okay.
The question has to do with when we get to critical sections. One of the things that we're going to do is if we have something that is really dangerous, we'll call that word critical. What I'm going to do is disable interrupts here. Yeah, that's setting the I bit equal to 1. And then I'll re-enable setting the I bit back to 0 again. And if this is running an ISR priority 3, if this is a priority 3 interrupt that disables the I bit, then what Mahesh is telling you is while I'm in this portion of my code, no interrupts can occur, even if it's a priority 0. Okay? So in the context of priority, you can force a section of code to run atomically. Atomically is this issue of being, once it's started, it will finish by disabling interrupts, executing the code, and re-enabling. So that's a good point. So the answer to his question is, as long as your lab partner doesn't disable the I bit, or as long as nobody disables the I bit, this is how the priorities will go. That's a good question. Any other questions about priority? Yeah.
How do you mark an interrupt is finished?
The question is, how do I mark an interrupt as finished? There's two things we do in an interrupt service routine. Well, there's a bunch of things we do in an interrupt service routine, one of which is to acknowledge, and that is to clear the trigger flag. We will see next time when we get to lab 3, there's a second option. Rather than clearing the trigger flag, we could disarm. So for instance, if I was interested in having exactly one interrupt, I could have it interrupt, and rather than clearing the flag, I could disarm it so it didn't cause any more interrupts. And then it turns out to finish an interrupt service routine, all I have to do is execute a BXLR. And we'll see why a BXLR, which is the regular, when you see a BXLR, what do you think of? Return from subroutine. Well, it's also return from interrupt. So I'm not sure which question you asked. Did I answer it? Yeah. Okay. Yeah. So the software will clear the trigger flag and just return normally, and that will automatically cause the context. We'll see it. I got a slide coming up. I mentioned this word ARM, and so if you think of the sequences that have to happen, the trigger flag is going to be set. That's the busy to done state transition. That's the event. That's the crisis. That's the alarm. That's a flag. Okay. We already saw clearing the flag is the software acknowledge. In the device itself, we're going to arm it. Okay. And so in the device itself, setting that, because there are hundreds and hundreds of flags. They all don't cause interrupts. And so we will specify which ones are important. We'll arm it. And then in the nested vectored interrupt controller, we'll enable it. Okay. And then the I bit has to be equal to 0. And those are the 4 things that have to happen for an interrupt to occur. Again, arming allows you to, in the device itself, in the I/O device itself, allows you to specify which flag bits will cause interrupts. And there's the trigger flag. That's the thing. If you want to put your focus first, put your focus on the interrupt flag. We'll see a bunch of examples of that. And as I said, the I bit in the processor it's actually in the primask register. That's one of those fun registers. It's 32 bits long, and it's got 1 bit in it. Okay, 1 bit down in bit 0. I equals 0 means enabled. I equal 1 means disabled. And just like a low priority interrupt, setting the I bit equal to 1 doesn't dismiss an interrupt, it just postponed it. Okay, just postponed it. So if you currently don't want interrupts to happen, you can disable them.
So is there an ARM bit for each interrupt, but there's only 1 enable bit for all the interrupts?
Yeah, the question was, I drew it. Yeah, it's still there. Okay. If you think about what happens if there's two trigger flags, okay? If there's a second trigger flag, there will be a second ARM bit in the processor, and there may be a second enable bit in the nested vectored interrupt controller, but there's only 1 I bit. Okay, there are some interrupts like your GPIO interrupt, the edge triggered interrupt, where there are multiple trigger flags, multiple arms, but only 1 nested vectored interrupt controller enable. Okay, so sometimes there's a 1 per 1 all the way here. Sometimes there's a 8 to 1. Okay, so the way to tell is you look at the vector. If there's a vector address for it, there will be exactly 1 spot in the nested vector interrupt controller. Did I answer your question? So the question was, how many of each do you have? And we have hundreds of trigger flags. Every trigger flag has a unique ARM bit, and then grouped by function, like the serial port, right? The serial port, all the interrupts through the serial port will go through one enable on the vector. But there's exactly one I bit. So the I bit disables all the interrupts in the entire processor. This is how we set the I bit equal to 1 as we execute this opcode. And this is how we set the I bit equal to 0. And you can see them here in startup.s as callable C functions. I listed this already, but if you think of the 4 things, it turns out these 4 can occur in any order. It doesn't matter what order they're in. We have to enable the device in the nested vectored interrupt controller. The exception to this is SysTick doesn't need this. SysTick does not have this step, but it has the other 3. We do have to arm it in the device. We have to enable all interrupts with the I bit, and then obviously the flag has to be set either on new input ready, output idle, or periodic or alarm. All right. We've mentioned this over and over again, but this is why interrupts are important and allows us to do bounded latency. We have a new input, and we'll see this. When I do Lab 3. I got a Lab 3 example for you next week, and I'll show you that I can run user code within a microsecond or 2 from you touching the button and still debounce the button. So that'll be a very low latency response that I'll set up for the keyboard, and we'll do that next week. And what we're going to do this week in Lab 2 is a periodic sampling on the A to D converter. And we're going to look at the time jitter. Okay? The time jitter is if I'm supposed to sample the A to D converter every 10 milliseconds or every 80,000 bus cycles, the question will be, when did I actually start the A to D converter? Okay, so what I'd like to have is Tn plus 1 minus Tn, where this is T1, T2, T3, T4, the time in which I sampled the A to D converter. The difference between those two represent the sampling rate, and I'd like to make this 10 milliseconds minus a delta to 10 milliseconds plus a delta. And this delta t is defined as jitter. Okay. There's some calculus involved in this, and that is if I look at a signal like this, what is the consequence? This is my input versus time. What is the consequence of a delayed A to D sample? Right? If I'm supposed to sample it here, right? That's the correct time, but there is a jitter, and I actually sample it there. What's the error? What's the consequence of a delayed sample?
It's too high.
It's too. I get the wrong answer. Okay, but you know, what if I have this? All right. This is when it's supposed to be sampled, and there's my jitter. I didn't get any error. Lucky. So what's the worst error I can have? Where is it worst? Where is the consequence of a time error cause the biggest voltage error? On the steepest spot. And so I can look at the consequence, the voltage error, by looking at the slew rate of my input and multiply it times the time jitter. So I will be able to map the voltage error into the time error, the real timeness of my interrupt into a voltage error. And that'll be, you'll see that in lab 2. All right, here's an example. This is actually data that I collected on my lab 2. I'm doing this right here represents the Tn plus 1 minus Tn, okay, which was supposed to sample at 100 hertz. Okay, I wanted to sample at 100 hertz. I wanted it to be every 8 80,000 bus cycles, I wanted to start the ADD converter. And this is a probability mass function of the number. I did it 1,000 times. Okay? And I measured this. Okay? How would I measure it, by the way? Lab 2 function. How would I measure? Right. Let's go to. This is the starter file for Lab 2, which is the ADD. This is a starter file from. So right here, you can see that this periodic interrupt is sampling the ADD converter. Okay, and I got a bunch of if statements in there because I'm going to cause a critical section later. Okay, see that? So if this is the time I start the ADD converter, how do I measure? If this is time Tn, right? This is time Tn. How do I measure that time? I can look at the clock, but somebody stole the clock off the wall, right? It's gone. But are there clocks inside of your processor? Yeah. So what I'm going to do is I'm going to set up a clock inside the processor that's just running along, and I'm going to measure what time it is now. Yeah, whatever. I'm going to measure it. Right? I'm going to measure it. That's Tn. And I need to set up a clock that measures it. It's going to not compile now, but I'm going to, and then what do? That's Tn. That's one of these. How do I measure the difference? I can look into the future. No. It's easier to do what? Look into the past. So let's do it this way. Tn minus 1. Okay, let's do it that way. Let's look at the time I did the last one and subtract it. And if I take the time in 2 subsequent times and I subtract it, I should get 80,000. And it turns out if you don't do anything to this program, you actually do get 80,000. I ran it 1,000 times. I ran that program 1,000 times, and I got 80,000 each time I did it. Hallelujah, it works. But then I said, well, what if, can I prove it always works? Okay, the question is, the only jitter caused by a single interrupt is going to be caused by which instruction got executed during the time of the interrupt. And we saw last time I mentioned 2 instructions that took more than 1 or 2 cycles. Remember what they were? There's some instructions that don't take 1 or 2. The branch takes 3. Yeah, the branch could take 3. It's the divide instruction. It could take up to 12. Okay. I said one more. No, multiply is 1 is fast. I said store multiple takes more than 1 instruction. The push multiple. It turns out push multiple takes so long that will actually interrupt that instruction. So if you think about it, if I push a whole bunch of registers on the stack, right? If I push 13 registers on the stack, how long is it going to take? It's got to take 13 cycles, right? 14 maybe. But that's so long that this instruction is actually interruptible. This instruction is divisible by the interrupt service routine. It's awesome. But divide is not. And so if I stick in a divide instruction in my main loop, I get a couple of +2s and a couple of -2s. Interestingly enough, I didn't get any -1s and +1s. Don't ask me why. It's weird and exciting. But I didn't. You will get weird stuff, and I want you to measure it. But we saw last time, if this is a priority 3 interrupt, what can cause its delayed function? I don't know. What priority is it? Let's go back and see what priority is it. It's a priority 2 interrupt. Okay, so I've set this up as a priority 2 interrupt. So what could cause a priority 2 interrupt to be delayed? 2 things. A bad lab partner who does what? Disables interrupts, bad lab partner. Or a priority 1 interrupt. Okay? If I have a priority 1 interrupt together with this priority 2 interrupt, and the priority 1 interrupt is running, what happens to this one? It gets it gets suspended, but worse, it gets delayed, right? It gets delayed. And so we see that here in this histogram. This one is, that's like a plus 50, right? Or plus 55, or minus 55. And that's a plus right there, almost plus 58. So I got quite a bit of time jitter caused by the presence of a higher priority interrupt. We're going to solve this in 445L in a very easy way. Well, we're just going to let the timer start the A to D converter so that we get no jitter. The second way to solve this would be what? Switch the priorities. Okay? Make this a high priority interrupt. But we'll be able to remove the jitter by learning a way for the timer itself to start the A to D converter. So it doesn't matter. You can have a lab partner who likes to set the I bit. That will not stop the A to D converter. So, all right. Whenever we build something as engineers, we want to say, who's the best? Who's the best? Right? You are, each one of you individually, but this is how we're going to measure it. We're going to do it by latency. Who responds the fastest? How many bytes per second can you establish? There is a word in the world called soft real time. An operating system, a system has soft real time if it has priority. If you can just say A is more important than B, that's called soft real time. In our case, that hard real time is bounded latency. Okay. If we look at a system, we can go through phases. If the bandwidth, the number of bytes per second being transmitted, is limited by the I/O device, we're going to call it I/O bound. If we see a input device and it causes an interrupt, and we put it into a FIFO, and our main program gets from the FIFO and it is I/O bound, the bandwidth is limited by the speed of the input device. What can you tell me about this FIFO? Is it going to be empty or full? Empty. It's going to be empty, right? So if the execution, if the software is fast, and the input, the hardware is slow, if I can process 1 million characters per second and I'm only typing 4, the FIFO will be empty. On the other hand, if this is CPU bound, in other words, I have a very fast, CPU bound is where I have a fast I/O, but a slow software. The bandwidth is limited by the speed of the executing software. What can you tell me about the FIFO? It's going to be full, right? And so this system, this data flow between the background and the foreground may go through phases where sometimes it's I/O bound, sometimes it's CPU bound. That was the purpose of the FIFO. And we could do the same thing with the output device. Again, if we have a main program and it is putting into a FIFO, and we have an output interrupt service routine which is getting from the FIFO, okay? And again, I/O bound means the bandwidth is limited by the speed of the output device. It's a slow printer, it's a slow whatever. I'm jittering a lot of data. The speed is not limited by software, it's limited by hardware. What can you tell me about this FIFO? If this is executing very, very fast and this is executing very, very slow, what will happen to the FIFO? It'll get full. Okay? On the other hand, if it's CPU bound, in other words, the bandwidth is limited by the speed of the software, I'm generating a very few characters per second, and I have a very fast output device, then the FIFO will become empty. Okay? And just like the input device, I may cycle between or may have phases where sometimes it's I/O bound, sometimes it's CPU bound. Okay? But this, looking at the size of the FIFO can help me visualize the status of my data flow machine. All right, let's do an example. This is the starter code for lab. This is the starter code for lab 2. It is essentially the 319K background sampler, except I'm using timer 0 interrupts. Here's the data flow graph. The signal is coming from some source. In lab 2, I don't care. Pick any source. You can do something simple like this, 3.3 volts. Put two 10K resistors right here. We're going to sample it. We're going to look at time jitter, all that sort of fun stuff. Here it shows it's cystic. It's not cystic. It's timer 0. All right. Yeah, see, timer 0. Okay. Let's show it to you. Let me see what's on the next one. All right. Here's a flow chart for the interrupt service routine, and let's go ahead and show you the code. All right. Let's start with a couple of easy ones. There's really nothing in the ADD. Yeah, question.
Why is timer 0 better than cystic in this case?
Oh, timer 0. Okay, the question is, why is timer 0 better than cystic? First of all, it isn't. It's different, and you learn cystic, so I want you to learn timer 0. The second way in which timer 0 is better is there's 6 of them. There's 6 timer 0s. Well, actually, it's called timer 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, so you got 6 of them. It's better because it's 32 bits. It's a 32-bit timer, which means it can go longer, right? Cystic is only how many bits?
24.
Cystic is only 24 bits. This is 32 bits. Yeah, we're going to need a bunch of them, so I might as well teach you timer, because there's only one cystic. There's nothing magical in lab 2. There's nothing magical about the ADD converter. This is exactly the same way we did it in 319K, but the timer is a new one. You remember Mahesh was talking about what happens if I disable interrupts, and this is what it looks like in the C code when I want to disable interrupts. Just like all the other TIVA devices, to use a device I have to turn on its clock, and then it takes a couple of bus cycles for that clock to become active, and so it uses a volatile variable here and reads the result just to wait a couple of bus cycles. Most of these devices don't like to be programmed while they're running, and so I'll disable the timer while I'm programming it. This is 32-bit mode rather than 16-bit mode. This is the mode for which it generates an interrupt periodically. This is the periodic interrupt mode on the timer. This is the rate in which it's going to interrupt. When I did my lab 2 measurements, I decreased that from 79 I took out one of the 9, so it went from 100 hertz to 1,000 hertz. Everything happened faster, 10 times faster, just making it quicker to take my data. So what used to take 10 seconds only took 1 second. There's the ARM bit. There's the ARM bit. That's the bit in the controller that says that the TO, the timer A timeout, is going to cause an interrupt. One of the things I do in my code is I clear the flag in the ritual. That causes the first interrupt to occur after the ritual and not during the ritual. And then I'm going to turn the timer on. And that's a typo. That's actually 32-bit mode. Okay. All right. So that now the interrupts are enabled and this timer is running. I can set up its priority. Everybody has a priority register. It's a little bit hard to find them, but when you do find it, there's 3 bits that you are going to set the top 3 bits of this register happen to be timer 0A. And then this is what I'm doing in the nested vectored interrupt controller to turn it on. So I'm enabling it in the nested vectored interrupt. You remember it needed the I bit equal to 0, right? And I didn't do it here because one of the good ways to use interrupts is to make sure all of your initialization occurs. All your variables are initialized, all your devices are enabled, and then after everybody's happily enabled, then you turn on clear the I bit. That way you don't get interrupts before the A to D converter is, right? So you don't get interrupts, and try to use the A to D converter before the A to D converter is turned on. All right. Timer. All right. So the interrupt service routine in this case is going to occur every 100 hertz. There's the acknowledge step. Again, this is one of those weird registers. This is a write 1 to clear register. And so the actual flag bit's in some other register, but if I write to the interrupt clear bit register, I write a 1, it clears exactly that 1 bit. So this is friendly. This guy here is just bit whatever it is. And it is a friendly operation. Yeah, question.
In the timer 0 initialization, isn't there also a TAPR register? How does that one work?
Okay, the question he says is there's a prescale register for these? Yeah, 32 bits is not enough for this guy. He'd like 48 bits. Go talk to the hand, all right? Okay, 32 bits is enough for me. There is actually a prescale register for this, so you can run 16 bits, 24 bits, 32 bits, or 48 bits. This is 16. I did. There is a prescale associated with this if you want things to get even more complicated.
Okay.
It didn't do it. Didn't need it. Didn't want it. There is. That's a good question. Did I answer?
Yeah.
Yeah. Okay. And so this particular step here will acknowledge the interrupt by writing, if I do a right click, go to definition of, you can see that flag is in bit 0 of the register. One of the debugging tools that I use is profiling, and there are 2 things of interest that I'm going to hook up to the logic analyzer. First, I'm interested in how long is it going to take to run the A to D converter. Get a sense how long it's going to take? Yeah, it's closer to 8 microseconds to sample it. And unless you turn on hardware averaging will actually make it occur very, very long. So once you set up the hardware averaging, so it takes 64 samples and averages them together and gives you 1, this is going to take 64 times longer to execute. Okay? So from a profiling standpoint, I want to know how long it takes to, how long it takes to run. And so the time between this edge and that edge, time between this edge and that edge is going to be the execution time of the A to D converter. The second thing I'm interested in is the time between interrupts. Okay? And so that's why I toggle it 3 times. So I'll be able to zoom out and see the sampling rate, zoom in to see how long it takes to run the A to D converter. And let's do that. Okay, I got the simulator on with the, again, I'd take your real data with the real board, but it'll run in the simulator. Okay, build, run. It's logic analyzer. Here we are. I've got it set up to, oh yeah, the main program is toggling. The main program is just toggling one of the other bits. The main program is toggling PF1. The background is toggling PF2 3 times. Run. Okay, stop. Zoom out. Okay? You can see from this plot sort of a general rule, and that is, what am I doing 99.9% of the time? Where's the most ink on this picture? Is there more green ink or more red ink? There's more green ink. So I can see right away that I'm mostly in the main program, and 10 times a second it runs the interrupt service routine. I can also measure the time between interrupts. Okay? And so let's zoom in. Okay, let's move it over here. Zoom in. Zoom over. This takes, oh yeah, I saw how to do it. To get this measurement, I'm going to set a breakpoint. I'm going to set a break. This is hard to do on the simulator. It's fairly easy to do on the real logic analyzer. I'm going to set a breakpoint there. Yeah, see, there it is. Okay. Now we can zoom in. Okay, let's try that again. Let's put the breakpoint over here. Okay, zoom in. Okay, clear. Okay, this is not working. Okay, let's try this again. Clear. Okay, run. There we go. There we go. Zoom in. There we go. You can see it now. You can see that the time it takes to run the ADD converter is about, should have been about 8 microseconds. All right. Questions on that? All right, let's go. So what you're supposed to see is a write to that register, the ICR register, to acknowledge the interrupt. I got 3 toggles to allow me to do 2 things to measure the execution time. But we have a potential problem. Is if let me zoom back out. I'm going to go over here. Okay. Let me shut off the breakpoints. Shut off the breakpoints. All right, so zoom out. Clear. Okay. So what can you tell me about the nature of the PF2 there? This top one, the red one. It's a square wave. You see that? All right. And now what I'm going to do is stop. I'm going to switch the program over so it does something bad. Okay, as you see this line right here. Okay, PF1 is a bit-specific addressing. Okay, and these 2 codes look very similar, right? They both toggle PF1, but I'm going to switch to the other one. There we go. So what I'm going to do is use the regular port to do the output. There we go. You can see it's no longer a square wave. Something bad happened. And what happened is what's called a critical section. Stop that. What bad happened is what's called a critical section. And what I have is a read modify write to a shared global, and that read modify write causes right here something bad happens. Right here in this instruction is the mistake, and that is when I read the value of port F into a register, I now have 2 copies of port F. I have the copy in the register and I have the copy in the port, and they're not the same. But when the interrupt happens, it gets the port over here, it uses the port value. And when the interrupt returns, it undoes the change caused by this other program. So we will see a critical section occurs whenever we share a global variable and whenever there is a non-atomic, a multiple step sequence access to that shared global, and one of them is a write. So it can be a read modify write, a write write, a write read, a read write. It can be a bunch of sequences with a write in it, shared on a single shared global, could cause a mistake such that the data becomes corrupted. Okay? So we will watch for this when we share globals with our multi-threading operation. Hi. So in summary, we have seen in this video how to use the timer 0A interrupts. And remember, it was 32-bit and it generated an interrupt at a periodic rate. We set the rate using the tail R register, and the particular bit which caused the interrupt, the trigger flag, was the TATO bit. And so we armed it and enabled the timer 0 to create an interrupt. We set its priority. It happened to be interrupt 19, so that we set the 19th bit in the nested vectored interrupt controller. And lastly, we had to clear the I bit to enable interrupts across the processor. In the interrupt service routine, we saw that we acknowledged by writing a 1 to the interrupt clear register. So writing a 1 to this register cleared the trigger flag in the RIS register. All right, and what we did is we caused the conversion. We asked the A to D converter to create an interrupt. All right, so we saw in this video that we use synchronization. Interrupts were used to reduce the latency. It was important for us to see some terms. ARM is a term that we have in the device which sets a trigger flag to allow it to interrupt. Enable is something we do in the nested vectored interrupt controller to establish or allow that to interrupt. We set its priority in the nested vectored interrupt controller. And then the busy to done state transition, or in our case, periodically, the timer flag was set. In the interrupt service routine, we acknowledged it, and we produced a real-time system by causing the A to D converter to trigger every 10 milliseconds. All right, so next we're going to look again at the critical sections, and we'll go on further.